Hello, everyone. We are QuantYantriki. And in this demo video, we will describe the user interface and code structure for the minimum risk portfolio generator application that uses a classical quantum hybrid algorithm to implement feedback assisted quantum annealing for hedging and portfolio optimization. So the end user interacts with what we call the minimum risk portfolio generator. This basically supplies user input to the quantum computational subroutines at its backend. Depending on the level of user access, these subroutines can run the algorithms on actual quantum hardware or on local simulators. So in order to design a portfolio, we can choose from a certain selection of stocks, and we can provide a date range over which the covariance matrix is to be calculated. In principle, the number of stocks or assets one can choose is unlimited. However, in this demo, we'll limit it to a maximum of 10 so that we can actually implement it on quantum hardware and compare both the QAOA, the quantum approximate optimization algorithms, and the quantum annealing algorithms under feedback. So here we show in green the user making a certain selection of stocks. Setting the date range. And so with the choice of the assets and the date range, the covariance matrix for model 1 is fully specified. When it comes to model 2, which is the alternate model, which can supply us partial information about the optimal portfolio, there are two modes for the user to input this information. One is to use the automatic prediction that the user interface provides. The other is to use the manual prediction mode. So essentially here, all the twos represent the fact that we do not have enough information to either choose or drop a stock. Choosing a stock would correspond to setting it to a 1, and dropping a stock would correspond to setting it to a 0 value in the portfolio allocation vector. The user can then choose a relative measure of confidence between the two models. So by setting this to a value of 1, for example, the user would say that the portfolio allocation vector must necessarily match all the partial asset choices that have been provided via model 2. By setting it to 0, the user is suggesting to the computational subroutine that model 1 is to be relied over model 2 completely. The user then enters the budget, and the budget should have enough space for non-trivial solutions. Setting it to a very low value would basically mean that we cannot choose too many stocks at all. And then once all these inputs are provided, both the models are fully specified, and then one can choose whether to use quantum annealing for the computational subroutine or to use the gate model for the computational subroutine. The final output is in the form of a recommended minimum risk allocation. Here, all the zeros represent the fact that the computation process suggests that we should not be picking these stocks. The green ones imply that we should be picking those stocks. The yellow one is confirmation that the predictions from model 1 and model 2 match as they should because of the feedback process.
Hi. So now using this code, I will solve a hedging problem on the D-Wave 2000 Q6 solver. So in the first block, what I've basically done is I've imported all the necessary packages. So in this line, with this line, what I have provided my API token and got myself connected to the D-Wave 2000 Q6 solver. So we have solved it for a particular case in this represented by M7 here, and the current prices vector as P7. So here we have made the uh, declarations, and we have taken the P convergence to be 0.9, and the future solution vector basically tells us the partial data or the model too. So using these, we have calculated the constraint matrix here, and using the constraint matrix and the covariance matrix, what we can do is we can find the Lagrange multiplier. Now, in order to declare a BQM object, what we have to do is we need to construct two quantities. First is the quadratic bias matrix. So this is the construction of this is shown in this block basically, and the second important thing is the linear bias vector, which is constructed here. And using these two, the quadratic bias matrix and the linear bias vector, we can create a binary quadratic model object, namely BQM1. So we have named it BQM1 here. After this, we have started a while loop till convergence. So when like this runs as long as convergence is not 1. The moment we want the convergence to be 1, and that is where we stop. So what we do here is we first store the sample and uh, the energies, and we find out the minimum energy. Then we sort the energies and find out the unique ones. So after finding out the unique ones and their frequency and probability, what we do is we calculate the marginal probability here in this block. After that, we check for convergence using marginal conditions on marginal probability and P convergence. After that, what we do is we run these blocks, and finally we move on to the final block. So this block is mainly devoted to printing the final solution. In the final solution, what we are doing is we are printing final probability, the final solution in the vector form, the future solution, and final cost and final risk. All the calculations are done in this last block. So I'll just run this code and show what's happening here. So clearly, based on our partial data, this is the final solution.
Hi, I will now be walking you through the code behind the QAOA. First, we import all the different packages we need to run this code, and we enable our IBM Quantum account. This is the QAOA function. As input parameters, it takes the covariance matrix that relates every stock in your portfolio. It takes the current prices of all of those stocks, the budget of the user, the future solution, which corresponds to information regarding which stocks you wish to invest in, which stocks you do not wish to invest in, and which stocks you're open to either option, and the probability of convergence, which is a threshold probability that the user defines. The residual cost is then calculated by subtracting the fixed cost that is going into any stock that the user has mandated must be bought. And we calculate a constraint matrix, following which we then develop a quadratic bias and a linear bias. The quadratic bias corresponds to any initialization or setup for our qubits that corresponds to the relation between any two stocks or any two qubits. The linear bias corresponds to initialization for each individual qubit. The total number of qubits utilized is nothing but the number of stocks in our portfolio, and n equal to 100 corresponds to the length of the circuit, or how many time steps we'll be having. We now run an iterative while loop until we achieve convergence. For this while loop, first we initiate our quantum circuit, and we initialize our qubits such that they are in an equal superposition and there is no bias. Then we create our problem quantum circuit. This circuit encodes the coupling of the qubits and the feedback to the qubits. The coupling strength corresponds to the gamma. The feedback strength corresponds to the delta. Following which, we then encode the mixing quantum circuit. This ensures that we are exploring the complete space and not missing out on any solution. The barrier commands essentially add a visual aesthetic to the circuit diagram. Following the development of the circuit, we measure every single qubit onto a register. And we decompose this entire circuit into basic gates that can be compiled. We select a particular backend. We can select an IBM quantum machine, or we can select a simulator. We transpile the circuit to ensure that there is compatibility with the chosen backend. We run this, we get the results, and we calculate the counts or the probability associated with every single result. Following which, this entire array is converted into a data type that can be processed. After processing, we create a list of all the solutions and we sort them in increasing order of energy. The least energy corresponds to the most optimal for the constraints we have imposed. We count the number of unique solutions. This corresponds to the degeneracy. And we create a list of all the unique solutions we have with the associated probabilistic weight and their energy. We then create an only solution. This corresponds to the list of solutions. We now calculate the marginal probability by comparing the solutions we have with the user constraints input upon the program. Following which, we then propose a feedback routine that then initiates a feedback system and proportionately rotates in either direction each of the qubits such that it can achieve the constraints that have been set upon them. After running this until we have achieved an optimal solution, we then calculate the cost associated with each of these solutions and the risk associated with each of these solutions. And at the end of all of this, we have achieved an optimal solution that has minimized the cost and minimized the risk. And we return this to the program.
So to summarize, we have created a minimum risk portfolio generator application that uses a classical quantum hybrid algorithm to implement feedback assisted quantum computation for portfolio optimization. This can potentially exploit quantum speedups in the risk minimization process while increasing the reliability and optimality of the return solutions from the quantum hardware. Thank you for your attention.